It's nice. I've been coming here since, 40 years now, since I started my master's in 1973 in Clarendon Provincial Park. So but the digs are a little different. And I'm not going to provide all the answers because I'm just as confused as I was 40 years ago about what controls ecological systems. But I'm now happier with that state of confusion. And I believe I'm confused somehow on a higher plane. And that's good because there's still all kinds of frontiers of ignorance for us ecologists to graze upon and keep our lives interesting. But something has changed over the last 40 years, and that's that things seem to be more complicated now. It's not just how many cottages can you put around a lake, how much SO2 can you put up into the air, should we allow that invader in or not. It seems that things are coming at us in waves in ecological systems, and that's making our lives more complicated. And the other complication is that it appears as if there's less understanding of the work that we do and the importance of the work that we do as scientists in contributing to environmental management, to the extent that we have federal politicians say things like, we don't change what we do based on a few additional facts. There seems to be less of a recognition of the interactive role of facts and values in the environmental management process. So when John asked me to give this talk, what I thought I would do is really address the non-bald, non-white-haired people in the audience, the young scientists that are entering the field, to give some advice about what's an applied ecologist to do in an increasingly complicated world. And I tried to reduce it to 10 lessons. There's many other white-haired, bald-headed people in the room would have had hopefully some similar lessons, but others would have been different. So let's see if this works. So if you're here, you're an applied ecologist. And what that means to me is that as a scientist, you want to understand patterns in the natural world, but you also recognize that man's hammer blow on the natural world can't be avoided. If you want to be a theoretical ecologist and never leave your computer, then increasingly the work that you will do will be less relevant to what's actually happening on the ground. So let's all, first of all, assume that we're applied ecologists. And what does that mean? It means that in addition to understanding patterns and processes and cause-effect linkages, at some point you're going to want to apply that work. So you're going to do several things. You're going to, first of all, attempt to detect environmental problems. That means that you'll look at a subset of all the possible indicators of environmental condition, compare those indicators, let's say it's lake trout abundance, with targets. You want to have this many lake trout in your lakes, and you'll report that on an ongoing basis so that you can tell society if there is a problem. So the first two missions of an applied environmental biologist or ecologist are to detect and report problems. And then hope somebody else also cares. There's this very complicated midrib where society then at large will consider your information about the state of, thanks John, I think I'll put it here. And see if they agree with you about whether a problem exists or not. If you can agree that we're all unhappy because the lake trout are gone, then society may come back to the scientist and say, why are the lake trout gone? What are the actual causes from among all the possible causes? So our third job as applied ecologists is diagnosis. If we can identify, the lake pH is less than 5, as John did in his PhD work many years ago. If the pH is that low, lake trout die. So then what should we do about it? So what are the links between, what are the quantitative links between cause and effect that will allow us to actually attempt to manage this problem in the environment? So prognosis then becomes our next job. What's going to happen if we do various things? And then finally, hopefully something is done, and we kick back in again, and now we have the last job that an applied ecologist actually does, which is see how the world has changed in response to human intervention. And so you can take these 13 little boxes and summarize my 40 years of work as an applied ecologist. And it was all great in the past. But then things started to get complicated. Let's think about identifying the stressor, for example. Well, there's a lot of stressors out there. And if I can borrow this slide from the health literature, it's often difficult to know what is the actual stressor that broke the health of the camel's back or broke the health of the camel. And similarly, it can be very difficult to understand which among dozens of possible stressors is actually responsible for the loss of those lake trout or environmental problems. So I'll give one example of that. So that's to show you that I know that that's true. And this is so important, I'm actually going to devote a few slides to this. Back in 10, 12 years ago, Lawler and his colleagues assembled the data from 181 species that were listed as threatened by the National Marine Service and the U.S. Fish and Wildlife Service of the United States. There were 59 different threats that were responsible for species being listed as endangered. And I pulled this data from that paper to suggest that on average, a species that was in trouble because of 4 different categories of threats. Not just 4 different pollutants, but pollution, habitat loss, invading species, and overharvesting. On average, it took, when species are really at risk or in trouble, it's the result of multiple interacting stressors. And those stressors vary around the world and in different biomes, which are the important ones. From Sala and a whole bunch of colleagues, 20-odd colleagues in their 2000 paper in Science, they asked the question, what are the biggest biodiversity threats for the year 2100? And if it's in tropical rainforests, we know it's land use change is the biggest threat. If it's the Arctic, we know it's climate change is the biggest threat. But things get more complicated in the lakes of the world because it's either land use change or the introduction of invading species are equally considered as threats. And in the boreal, where we almost are now, they realized that there was all kinds of threats that might have been a little less intense, but there was more of them. Land use change, climate change, and a contaminated atmosphere were all responsible as threats. So we must consider, it's no longer acceptable to just say, I'm going to work on acid rain, well, it might be acceptable in the tropics to say, I'm going to work on land use change, and we're going to ignore these other things. But when you're up in the boreal, we no longer have that option because there are multiple stressors that are threatening our life. This is why I'm confused, personally. So in my own working life over the last 35 years, I have proven unequivocally that animal plankton communities of lakes are affected by everything. They're affected by changes in phosphorus, pH, calcium, chloride, and metals. They're absolutely affected by ultraviolet radiation that kills Chaabris, by wind that affects their distribution, by temperature that affects their growth rates. They're absolutely affected by accidents of location on the landscape. They're absolutely affected by competition for food that's good quality. I had 2 wonderful years working on parasites. Zooplankton are absolutely affected by microsporidial parasites. We ignore microsporidial parasites of plankton, we might miss what's actually regulating population dynamics. They're absolutely affected by fish. I saw Charles in the audience. They're absolutely affected by Chaabris and other invertebrate predators. My God, they're affected by chemistry. If you don't know something about chiromones coming from other kinds of predators, you're going to miss what the important factors are in zooplankton. They're absolutely infected by invading predators. They're absolutely affected by hybridization and selection operating at time frames that are almost as fast or perhaps as fast as the responses to chemicals. And all these darn things interact. So the world is complicated. Great opportunities, lots of ignorance here to graze upon in your future work. I just want to prove, using an old Sudbury data set, that interactions happen and can be really important. So 30 years ago, we published 2 little papers based on work with Claude Lafrance in the Ministry of the Environment back then. I think Claude is retired from the MOE now in Sudbury, where we asked this question, do nutrients affect acid lakes in the same way as they affect non-acid lakes? And this was to test Ole Grahn and Hans Holtberg's oligotrophication hypothesis, which was a big, important paper published in 1974, as I recall, in the early acidification literature, that basically said it's not acid that's the cause of the problem in many cases. It's actually that acid lakes process nutrients differently. So we thought we could test that. Well, what would you hypothesize for zooplankton biomass if you add nutrients to an acid lake? Adding nutrients generally increases biomass. Adding acid generally has little impact on total zooplankton biomass because you lose the sensitive species, but there's functional redundancy, and the tolerant species will rise in abundance. So if anything, you might think the joint effect might be neutral or there should be more zooplankton, but I don't think you ever would have predicted this, that in the first year there was an explosion of biomass. It's an acid lake, so there's only 2 species. a little cladoceran, a little copepod. By the middle of the second year, all the crustaceans disappeared. There was an explosion of rotifers. By the third year, we lost all zooplankton in the lake. So you never would have predicted that adding nutrients, I don't think, would have ended up killing off all the animal plankton unless you looked at the ecology. And this is the phantom midge Chaabris that was responsible for all of these changes. And normally its abundance has 4 instars. The last 2 instars are controlled by fish. The first 2 instars are controlled by starvation. This was an acid lake, no fish. We added all this food, no early instar larval mortality. By the third year, we had a lake that had only in it phytoplankton biomass and invertebrate predators, nothing else. So these things can interact. And these days, this is one of my just a little example of why these interactions really matter. So all over the Canadian Shield, there's a switch going on in animal plankton from calcareous plankton to jelly-clad plankton. So here's a handful of a jelly-clad species called Holopedium, just pulled out of a net haul from Plastic Lake. And I'm struggling right now to figure out what's going on here. And it's complicated. It probably is something to do with the fact that logging and drought and acid rain have changed calcium saturation in soils and thus changed calcium levels in lakes. And Holopedium only needs 1/10 as much calcium as Daphnia. Or we're losing phosphorus for reasons we don't quite understand, and Daphnia needs twice as much phosphorus as calcium. Or DOC levels are rising, which protects Chaabris. And Daphnia is more sensitive to Chaabris than Holopedium is. Or maybe it's the invading spiny water flea which eats all 7 of 8 Daphnia species but can't touch Holopedium. So the world is actually getting more complicated and fascinating. And everyone should learn structured equation modeling because you can actually sort of begin to tease this sort of stuff out. So what's an ecologist to do when there's multiple stressors that interact, when there are many possible responders which also interact, and the stressors and responders and their interactions differ from place to place? So in other words, when things are really getting complicated, should you give up and become a real estate agent? So first thing you should do, I think, is recognize the history of ecology a little bit. And that's that we went into this field because we love complex systems. We're ecologists. We're not deterred by the fact that the true complications, the true complexities happen at the level of biodiversity in our lakes. I have no idea how many species there are on a lake, but it will be something like this, millions of bacteria, tens of thousands of protozoa, thousands of phytoplankton. I asked Ken Nichols once how many phytoplankton species there were in a lake. He said, my guess, 5,000, Epibionts, something we never worry about, but every living creature out there is a habitat for some other creature, and there's thousands of epibionts. Certainly tens to not hundreds of macrophytes, hundreds of zooplankton. And all of these numbers are too low because they're based on traditional taxonomy. Because the first time we've used pyrosequencing techniques to ask how many zooplankton species are there in Hamilton Harbor, we came up with a number that was 50 times higher than the known number of species. So either our pyrosequencing techniques are wrong, or we really are missing all kinds of cryptic and rare species in lakes. So we're used to dealing with complexity. In fact, we revel in it. And my best proof of that is a comparison of the citation rates of 2 really classic papers. So G. Evelyn Hutchinson's 1961 Paradox of the Plankton paper has been cited about 1,500 times. 1,500 times. If you have 1,500 citations in your career, you're doing well. This paper by Hutchinson was cited 1,500 times because it attempted to answer the question, why are there so many species of phytoplankton when we know competitive exclusion appears and the lake appears to be a relatively homogeneous habitat? 20 years after that, Rigler published this brilliant, wonderful paper that basically said Hutchinson was wasting his time. He didn't say that, but that this desire of ours to understand biodiversity and work at the species level is misguided. It's impossible for us to actually do that kind of work. And this paper's been cited 76 times, so you know that as a discipline, ecologists have just ignored that advice because we revel in the natural complexity of ecosystems that we want to understand. But everyone should read this paper by Rigler's, even though it's hardly ever been cited. So we're very happy with complexity, I would argue, but we're less happy or more confused by all these ecological complications. And there are 5 basic types. related to stressors of ecosystems, anthropogenic stressors of ecosystems. There's changes in habitat chemistry, we call that pollution. Changes in habitat geography, we call that land use modification. Changes in habitat physics, we call that climate change. In augmentation of natural death rates, we call that harvesting. And then we fiddle with gene pools and colonization and immigration rates, and we normally call that, non-indigenous species introductions. So these are the kind of complications we normally deal with today. So given that, that's my introduction. So what I want to do today is give you 10 bits of advice, mainly to the young people in the room, in this increasingly complicated world where we can't just focus on one stressor anymore, in which multiple stressors are the norm, and critically, in which there appears to be increasingly less understanding and support for the work we do and the role of the work that we do in the national policymaking. I encourage everyone to buy this book called Fool Me Twice, Fighting the Assault on Science in America. It's a really remarkable book on what's happening to the appreciation of science in the world. Okay, here's my 10 bits of advice that I'm going to spend the next 40 minutes talking about. Work, I recommend that every applied ecologist work within the confines of some sort of environmental protection model, like the one I showed you earlier, the 13-box model. I'll just read them here and then we'll get it. If our first job is to detect problems, that means we need targets. And my second bit of advice is to recognize that there are no fixed targets. The targets actually change. I'm going to encourage everyone to work to embrace multiple subdisciplines. Bill Keller and I talked about this about last night, and for 30 years we didn't have to do this, but now we do. We have to be prepared to embrace multiple subdisciplines in our work, and as we're doing that, we should recognize that many conventional methods are often inapplicable to the work that we do. I'm going to encourage everyone to be a limnologist in their approach to applied ecology, and limnologists recognize they have to be physicists, chemists, and ecologists, and perhaps hydrologists and wastewater engineers. You have to learn everything you have to do that affects the ecosystem you're studying. Then I'm going to sort of become a little bit more political and talk about the importance of communicating. I have to do that less here than in many labs. This is the point I'd like to talk to people most about because I think we need to track different kinds of indicators than the ones we're doing now. And the other three you can read. And I'm going to end being a little bit political. So, first advice. I think everyone that's an applied ecologist should admit that you're an applied ecologist and then develop some sort of environmental protection model that steers your work to some extent. This is not a cop-out to be applied in your work in any way. Some older ecologists will tell you that it is. You come to a university not to understand things, not to fix things. So I'll just remind you that the two top aquatic ecologists in Canada, John Small and David Schindler, all of their lives have been applied ecologists, trying to solve problems and learning things while they're doing it. So ask, and no lesser lights than Paul Ehrlich and Gretchen Daly, even 20 years ago when they talked about the role of science in the environmental management process, said that this is what we should do. So ask yourself these questions. Is the environmental issue known? If not, will your work actually contribute to the detection of large-scale environmental problems that are serious? Ehrlich and Daly called that problem perception. If the problem is known, are the causes truly understood? If not, will your work identify the causes, the actual causes of that problem from among the universe of possibilities? Ehrlich and Daly called that mechanistic understanding. If the cause-effect linkages are understood well enough to inform management, are the cause-effect linkages understood well enough to do something about them? If not, will your work provide that understanding? Ehrlich and Daly called that strategic assessment. So there's nothing wrong with thinking ahead. There's enough fascinating problems in the world that you can tackle problems that also will allow you to be an applied ecologist and make a difference in the world. And if you do, like John Small and Dave Schindler, at some point you'll be in the newspapers all the time and things like that. Second thing, once you decide that you are an applied ecologist, your first mission is to see if the world is in good shape or not. Your first job is to detect problems. And that means you need indicators, and you need targets. So the next thing I want a bit of advice for you is to recognize that targets may change. And Bill and I, and more recently John and I, have been worrying about this, that if targets change, and the industry asks you or the city asks you, has the system recovered or not, then that's, that having really good targets that you understand is very important in answering that question. So a long time ago, in 1974, I think this picture was taken. Bill, do you remember? Or 75 or something? On Middle Lake, lime was being added to Middle Lake in the fall of '73 for the first time. And then every 10 years or so, Bill and I will write a paper on how the lake is doing. And then John and I will write another one on this probably next year. And increasingly, we're getting nervous because our targets are 25 years old. So finally, we've addressed that. Michelle Palmer did her PhD with me and revisited all the same lakes and developed new targets. And here's why it matters. So here's this data set of the recovery of biodiversity of animal plankton in Middle Lake from 1973 to today. And up until very recently, we've only had this 1980s target. And here's the bottom end of that target. It was 8 to 12. And we said that the lake has recovered. But recently, using this new target, the target is now 10 to 14. The lake has not recovered. And so it's very important to be very clear about the targets you're actually using and what they mean. So this, with Bill and I and Michelle, this paper is now just in press. It was interesting. The reviewers of this paper said, well, we all know this. You know, we all know that targets can change and you have to revisit changes. But then both reviewers said, but you know, I've never seen anyone actually prove this, you know, that targets really do change. It makes sense, but no one's ever shown that these targets really have to be updated and can change and that actually might influence management decisions. So well done, Michelle. My third bit of advice is, I actually don't have to tell this to the young people in the audience, but I'm kind of reminding myself what older ecologists have had to go through, to embrace multiple subdisciplines to help you solve your problems. I took this graph from Jana Altschuler, who did her honors thesis with me on what's it called? So the effects of low calcium stress on the up and down regulation of calcium-related genes. I knew absolutely nothing about what she was doing, but I knew it was worth doing. And so she has gone on to finish a master's on the same question. I had started as an ecologist, but over the last 10 years had kind of become a toxicologist to the point where Kathy Eimers introduced me at a conference once as an ecotoxicologist. I wore that label as a brand of honor because it meant to me that other people out there thought I'd actually managed to link these two fields. But I think we need to link many more of them. And so we need to become ecotoxic. We need to get into ecotoxical genomics and ecological genetics. And we need to recognize that speciation and adaptation can happen at speeds that are relevant to environmental management. So we need to embrace the reality of the true universality of modern biology in our work. Here's just one tiny example in my case. The name Michael Artz got mentioned this morning. Michael Artz is one of the world's foremost experts on aquatic lipids. Did you all know that the lipids we can see because of the environment? Without these aquatic lipids, we'd be blind, stupid, hungry, and dead. So that's just blind, stupid, hungry, and dead, right? 20% of our brain is lipids, and the vast majority of that is omega-3 fatty acids that come from the water. In the water, where does it come in the water? It comes from diatoms. When we lose diatoms and gain chrysophytes, there's a 10-fold reduction in these desirable omega-3 fatty acids. This stuff really matters. The same fatty acids that are in the eye spot of an amoeba are the same chemicals as are in our retina. So these things were so valuable, they've been preserved throughout evolution. So we thought we'd ask this simple little question. When you look at a spiny water flea, here's a spiny water flea from Harp Lake. It looks like it's full of fat. You know, it's kind of yellow and orange, and it looks, you know, if you could carve away the skin of my stomach, I think that's what you'd see. And lots of fat. So we said, well, might the lipid levels in the algae actually influence the spread of an invading species? So we did a little experiment. We added, EPA, you know, when you buy your shark oil tablets or your fish oil tablets, you're looking to maximize the EPA and DHA content. The eicosapentaenoic acid is the EPA. So we enriched it in the algae, and then we fed that enriched algae to Daphnia, and then we fed the Daphnia to the spiny water flea. And sure enough, just adding this one lipid increased the body weight by 20%, increased the fecundity by 50% in the spiny water flea. And we'd only managed to get the EPA level of the spiny water flea from 5% to 7%. Not very good, actually, because when we went to the field, it was 23%. So 23% of the lipid in these animals was actually this 20-carbon long-chain essential fatty acids. So suddenly, I'm recognizing that to understand the spread of an invader, We have to become a physiological ecologist and learn something about lipid chemistry. That was a real shock to me. So consider and talk to your colleagues down the hall. Don't let your departments split up. Keep your physiologists, your molecular biologists, your ecologists all working together. And we need those sorts of interactions in the world today. When I became a toxicologist 10 years ago, I fairly quickly realized that there was a problem with Daphnia toxicology. So here's my lesson number 4. And the problem is that the entire focus prior to that date of Daphnia toxicology had been to set regulatory standards to allow the regulation of industrial discharges so that the environment would be protected. There's nothing wrong with that. Nothing wrong with that at all. And it's supported there are professions, there are laws, there are university curricula, there are dozens of journals where all the work of regulatory toxicologists is published. Is that work useful to actually explaining the changes that are happening in the environment? Well, it may be, or it may not be. And it may not be, because if you look at the conventional Daphnia toxicology literature, you find that most people work on one clone of a species that doesn't exist in Ontario. They feed these species to saturation when they're always starving in nature, and there may be a link between whether you're starving or not and how well you can resist stressors. They feed them with green algae, which are not bad. It's not as good as salmon, but much better than Twinkies. But because it's not that good, it's often supplemented with things that a Daphne would never see, and with cereal crops and things like that. And the assays normally last 2 to 4 days. When a Daphne doesn't mature and start to produce eggs until 6 days or 8 days, so we're missing this very sensitive life stage. Most of the work is done in hard water, which is great. There's a lot of hard waters in the United States. There's a lot of soft waters in Canada, so it may not be applicable. All this work is done usually at one temperature for regulatory toxicology. And our lakes aren't at one temperature. They're all over the place. So how useful is this for an ecotoxicologist? It may be very useful, but you must examine it before you just assume it is. Here's just one little example of where you may be led astray by conventional toxicology. I thought I'd pick road salt as an example. So we salt our roads in eastern Canada. I guess they're too cold in Manitoba to salt them there, but we salt our roads here. So in Muskoka, we have a couple of lakes where the cottagers have turned their homes into homes, and the road's been paved. And most of our lakes, sodium levels are kind of constant, but in 2 of the lakes, sodium levels are going up. That's a road salt effect. But the levels are still pretty low. By comparison, so the chloride equivalent of this won't be too much different. And the chronic guideline in Canada for chloride is 120 milligrams per liter. Okay? So we're still a long way away. But let's drive up to Sudbury. And I'll thank John and Jocelyn for sending me the chloride data from the last 10 years just last week. So here's the current Canadian water quality guideline for chloride, 120. Things change rapidly in the world. So when I started working here in the early 70s, Hanna, Middle, Clearwater, and were all typical northern lakes with less than 1 milligram per liter of chloride. But you look where Hanna is now. It's occasionally up to 110. It's sort of stabilizing at around 80 to 90 milligrams per liter of chloride. But it's below the 120, right? So everything is probably okay. But these bioassays are done on Daphnia magna. They're done in hard water. They're done at saturating food levels. Might there be any reason to think that if the animals were starving, they couldn't cope with that amount of chloride? And is there any reason to believe that food levels are falling? I didn't ask you for the phosphorus data for Sudbury. I should have. But in Muskoka, phosphorus levels are falling from low to lower. And I assume that phosphorus levels in most of the lakes up here are pretty low. Might there be a link between food levels and chloride toxicity? So I have a new student in the lab who's addressing that question, Aaron Brown. So you saw earlier in the talks this morning, the toxicity talks, where LC50 was on the y-axis, and usually DOC was on this axis. So here's the link between how much food in milligrams of particulate carbon you're giving to Daphnia and what their sensitivity is to chloride. So as long this is saturating food levels, 1 milligram per liter of carbon saturates the ability of a Daphnia to take up food. So at that level, at 1, you're okay, because you're up at the LC50 is 200 or 225 milligrams per liter. But just drop the food levels down to 0.4 milligrams per liter particulate carbon, and suddenly the LC50 is 75 milligrams per liter of chloride. So I believe right now it's very possible that Hanna Lake the animals in Hannah Lake, one of the reasons that we haven't considered before for the slow recovery of Daphne in Hannah Lake is the road salt. And so that's worth exploring. Okay. Lesson number 5. And I want you to treat this as a great opportunity for 40 years of interesting work in your careers. Please assume that physics, chemistry, and ecology all matter. John mentioned that this morning, and I want to now prove to you that it's true, that physics, chemistry, and ecology all matter. And I'm going to do this with reference to the recent work we're doing in our lab on calcium decline. Okay, so Adam Jaworski and Don Ashworth were my 2 first master students working on calcium decline, and Adam went out to 9 different lakes that vary widely in calcium in Ontario and asked, does some little microscopic crustacea need more calcium than other little microscopic crustacea? They're all crustacea. You know, they all molt. They're all supposed to be crunchy. But it turns out that the Daphnia ambiguicatava mendoti pulex, have much higher calcium requirements than an animal like Holopedium, which is that jelly-clad animal, which needs 20 to 50 times or maybe even 100 times less, has a lower requirement for calcium in its body. So that got a bunch of us started, and it's kind of culminated with Allegra. This is Allegra Cairns' master's thesis, to ask, is there a link between calcium level and the frequency of occurrence of a bunch of Daphnia species in 311 lakes in Ontario. The solid line is kind of a Gaussian logistic fit, but I care much more about the dashed line in the background. So we sorted the lakes by into 20 different. We sorted lakes by calcium, got 20 different groups, and then calculated the average frequency of occurrence of that Daphnia species in that group, and that's what those data points are. It's kind of like a brute force XL calculated logistic regression. So what you can see for this species, for example, is it's found in 50% of lakes as long as the calcium is higher than 2. But if the calcium is approaching 1, it's only found in 10% of the lakes. And we have 8 species of Daphnia, and 5 of them have this, 6 of them have this pattern, 2 of them don't. So we thought we'd made the case. We also brought these animals into the lab and lowered the calcium and showed that they all died when the calcium was low, or they grew a lot slower. That this was a simple example of a direct chemical effect on Daphnia. And then we started talking to Howie Risen, and Charles, who collectively have spent their lives working on Daphnia K-Arbus interactions. And Howie said, you know, Norm, it's possible that there's another mechanism here, which is that the calcium stress is weakening the ability of the animals to deal with their predators. And that's because in the face of chemicals in the water, so-called chimeromones, that mother Daphnia detect, their babies are bigger at birth, and their babies grow more rapidly to allow them to escape being eaten by K-Arbus. Their carapace actually gets more rigid in the presence of K-Arbus, and maybe calcium is needed to make that carapace more rigid. They produce ornaments on their shell of several different kinds, but the 2 most common kinds, probably many of you have seen pictures of the big helmet that Daphnia get on the top of their head. That actually alters the pressure field as the Daphnia swims through the water. And these K-Arbus actually have big eyes, but they don't use their eyes to hunt. They use sensory neurons on the side of their body to detect pressure waves. And when the Daphnia have this big helmet on the top of their head, it alters the pressure wave, and the K-Arbus miss them when they strike. Others produce these neck teeth. Other species produce these spines on the back of their neck, which don't reduce capture efficiency, but dramatically reduce ingestion efficiency, because they're a gape-limited predator. They try and stuff this predator into their mouth, and it gets stuck on these teeth. And so we set out to investigate this. The paper just came out in PNAS, so we're very excited. This is the only time in my life I'll use something called the Young's modulus. So a Young's modulus is a measure of the rigidity of a spring, the rigidity of a spring. So when you have a surface that's behaving like a spring and you press on it, how much does it resist that pressure? And we had these mad German engineers we were working with that were measuring that with some kind of fancy confocal microscope at 20 points and 100 micron by 100 micron grid on the side of on the flank of a Daphnia that we'd reared at 4 different calcium levels with and without the presence of the K-Arbus chemicals. And at 5 milligrams per liter of calcium, the rigidity doubles in the presence of the chimeramone. But at low calcium, the carapace is not more rigid in the presence of the same chimeramone. And at high calcium, without the K-arbus chimeramone, it's also not more rigid. So this is an example where the calcium prevents a normal response to the presence of a predator. They also produce those cool neck teeth. The neck teeth don't work for first instar animals because they can't make them long enough, and the animal is still always too small that it's going to be eaten. The neck teeth don't work for fourth instar K-arbus, day 8, because they're already big enough that the K-arbus can't stuff them in its mouth. But for instars 2 and 3, half of the juvenile life of the Daphnia, there's an enormous benefit to having neck teeth. And you can see that the neck teeth are much shorter at 0.5 and 1.5 milligrams per liter of calcium than at 2.5 and 5. So this is another way that there's an interactive effect of calcium and the chimeramone, and the calcium is preventing the induction of a defense. The last one is growth. I stupidly reversed the colors of the, so in this case, the clear one has the chimeramone. So they're at 2.5 and 5 milligrams per liter. They're a lot bigger in the presence of the K-arbus chimeramone. But by the time you get down to low calcium levels, they can't get bigger. So this is an example of the interaction of chemistry and biology that matters for the life of an animal. So they suffer at low calcium. We initially proved that this was just because their growth, reproduction, and survival was reduced. But also, there's an ecological part that matters. Their ability to produce their normally effective defenses is also reduced. So you can't forget, it's not just pure chemistry, you have to look at the biology too. And this also plays out at a regional scale. This is the last paper from Michelle Palmer's thesis that's currently under review. So we had a whole bunch of lakes. Each of these dots is a lake that were sampled once a month for a whole year. We did this in the 80s when I worked with Keith and Andrew and Peter Dillon at the Ministry of the Environment. And then Michelle went back in 2004 and 2005 for her PhD, actually before she started her PhD, and repeated these analyses, monthly sampling from 40 lakes for a year. And first of all, we're getting new targets that Bill and I and John could use, but we're also asking, have the communities changed at a regional scale? And abundance was lower. Species diversity was higher. Most of the data points are above the line. Species richness was higher, substantially higher. You know, here's a lake that had, this is, say, 5 species in the 80s. Now it's got 9 species per average in a collection. There's a huge increase in the abundance of large Daphnia and a reduction in the abundance of cyclopoids. So there's all these changes happening across the region. Some of these are pretty simply explained by bottom-up effects. I mean, the total abundance of zooplankton was lower, and that was correlated with less phosphorus. Pretty simple, nothing else correlated with that. After that, things get a little more interesting. The abundance of large cladocerans, Daphnia, was clearly much higher. Most of the data points are above that 1-to-1 line. And that was correlated with falling phosphorus, falling temperature, and chloride. So what I want to mention is there's a physical and a water quality effect there, and both are supported by the literature. So at lower nutrient levels, bigger animals, because they have a lower metabolic rate per unit mass, have a lower starvation threshold at which they can maintain life. And there is a very large body of literature that indicates that poikilotherms grow slower but end up bigger at maturity in colder water. It's seen so often that it's actually called a law in some old papers. So for this metric, the importance of large animals, you need to look at both temperature and nutrients. What about biodiversity? We all care so much about biodiversity. Here you have to look at everything. So the species richness had clearly increased. This is why the target increased by 20%. On average, there's 20% higher richness of zooplankton species in these lakes. That was correlated with recovery from acidification, with rising temperature, in a few cases with rising phosphorus, but was only observed when there were no spiny water fleas. So when there were spiny water fleas, there was no significant change. So that in the richness over that 25 years, so you have to look at chemistry and physics and biology to understand biodiversity. Okay. So now my more political parts. So the first thing I'm going to recommend is you engage with the public. This would have been quite an alarming thing to say 20 years ago, because 20 years ago, Bob Lackey, who was a senior advisor on the National Precipitation Assessment Program, I think Bill must have met him and John must have met him, he wrote a bunch of papers, Science Policy and Acid Rain, in which he was saying scientists should stick to the science, stick to the facts. You'll lose your credibility if you don't just stick to the facts. Jump ahead 20 years, Reed Noss and others have countered that we actually have a responsibility as scientists. So as scientists, how should we engage with the public? Well, obviously, we should not abandon engaging our peers. We still have to publish and communicate and go to conferences and that kind of thing. But there's many other things I think we should do, and I've just listed some of them here. Support citizen science, support NGOs like Learning for a Sustainable Future. I've started working with this NGO that actually works to produce high school curricula, to take science and arts and translate it into high school curricula. Brand your lab. I've slowly realized, without knowing it, I have a brand for my lab, and if anyone's interested, I can tell people what it is. Develop curricula that are interdisciplinary. Teach as if your students will not be academics. Most of your students will not be academics. And here's one I want to focus on. Add outreach projects to your multi-PIN, sort of PI answer grants. Join the Coalition to Save ELA. I'm thought of actually in my little town of 15,000 as the town kook in some ways, but also the town scientist. People knock on my door and say, "What's this spider?" And and I always jump back because I'm scared of spiders when they do that. So here's just an example. Shelley and I have got lots of funding for the Canadian Aquatic Invading Species Network. Now we're in our 7th year or something. The first 5 years, I just did science, and we sampled those 311 lakes. We tracked the spread of the invading species. But I'm much more interested in the second one. I'm still doing some science with Shelley, but Shelley is leading. But the project I'm leading is this one, where we're reviewing national policies that will promote early detection and rapid response of invading species. The postdoc who's doing this, Andrew Smith, has written the brief that MNR has used on the inadequacies of the legislation in Ontario to deal with invading species that's gone to the higher authorities in MNR. We're reviewing secondary school curriculum on invading species. That's what we're doing with Learning for a Sustainable Future. We're going to review media coverage, how well is the public being informed? And we're going to develop a course. So NSERG funds this. So it's actually possible to raise money in NSERG as a biologist to do work that you never would have thought you would get funded for in the past. And that's wonderful. Okay. This is my advice number 7 is the one I would most like feedback from ecologists that are better than me. Because and John and I have started to talk about this kind of stuff. I think this is unbelievably important, and I don't quite know what to do about it. And that with all of these stressors out there, they can sort of interact. It's kind of a bit like realized niches and theoretical niches, Hutchinsonian niches from the old days. That many stressors will have an impact on organisms, but it won't show up immediately as damage. But it will weaken their ability to deal with other stressors. And we need to start tracking that. And that's because when change happens, it can happen quickly. Look at Carpenter's book on regime shifts. And so others, much smarter than me, like Steve Carpenter and others, Folke, it doesn't matter their names, but worked in this Resilience Alliance concept that when things are really complicated and regime shifts happen quickly, we need to understand the antecedents for those regime shifts so that we can prevent change before terrible change happens. For example, I do a lot of work on calcium and phosphorus decline. And those aren't toxins, but they may very well weaken the ability of organisms to deal with other stressors. Okay, so I'd say these ideas are my least developed, but I really like this paper by McGill that was sort of a good start in this area. So we're beginning to work with John in our lab to look at body condition, lipid reserves, stress hormones, metabolomics, to begin to understand whether organisms are in stress and thus might be more vulnerable to other stressors. I think that kind of work is very important work. This is silly, but you should all remember, how many people were at the talk I gave here last year on science writing? Is there a show of hands? Okay, so remember one of the things I said is jump at opportunities. The most interesting papers are the low-hanging fruit, that you get this great idea and you can do that work. So there's great low-hanging fruit out there right now. In Muskoka, our lakes are freezing 3 weeks later in the fall. We know nothing about autumn limnology. There's a great opportunity to start doing work on autumn limnology. Shallow lake limnology, incredibly important. The effects of warmer water on everything. We need to be doing this. The effects of long droughts. We talked about droughts this morning. All of these things that we can see are happening. Please embrace these things that are happening on the landscape rather than doing traditional kind of old-fashioned stuff. There's no one in the room who does old-fashioned stuff anyway, so. Okay. So here's my simple view of the world. To solve environmental problems in a working democracy, we're going to have a little discussion about what a working democracy is, you need really only two things. You need only two things. You need knowledge and the will to act. In theory, we get this knowledge from science. You need to know you have a problem. You need to know that what the causes of that problem are. You need to link the causes to the responses in a way that you can inform management. So up to a point in that environmental protection model, you need knowledge, right? You also need the will to act. You don't need money. It's not on the list. We've got lots of money. We can solve climate change for the cost of the Iraq war. We chose to go to Iraq as a world. We chose not to solve climate change. We make choices. So it isn't a money issue. It's a will issue. So where do knowledge and will come from? Here's one of my favorite quotations that people have seen me use before. It comes from a Canadian poet, Richard Outram. I heard him say this on the CBC one day. The cardinal human values are humility and hope. Cardinal human values are humility and hope. That phrase is stuck in my mind, and it's never left. So, my God, we should be humble, because we got it wrong so often. We've screwed up so often with the world. Individually, we're pretty dumb, but collectively, we're pretty bright. So we should be humble enough to realize that collectively, we have the answers, or can have the answers. And so one of the absolute underpinnings of knowledge is humility. The only certain mind is the arrogant mind, right? If you're certain, if you understand everything, you're bound to screw it up. Hope comes in part from knowledge that you've fixed enormous problems in the past. The problems in the past that were the biggest ones that started the environmental movement were DDT and the loss of songbirds, acid rain, lead pollution in children's health, first reported deaths of the Great Lakes. We've kind of gone a long way to solving those problems, so there's cause for hope. There are other roots of will. Experience is another great root of will. Wanting to have your children survive in a happy world is another root of will. But we need a kind of counterbalance for this, so here's my made up kind of, if we have cardinal human values, we also have cardinal human flaws. So I would assert that the cardinal human flaws are arrogance and despair. Maybe I'll just leave that the way it is. The cardinal human flaws are arrogance and despair. Arrogance isn't so much a choice, but despair is a choice. And something else to recognize is that there are people out there in the world that want us to be in despair. So we should choose to not be. It is absolutely a choice. And if you fall into despair, despair is no basis from which to solve anything. And there are people that would like that to be the case. So all great things have been said once in the past. So here's three great questions that were asked over 2,000 years ago by the Babylonian rabbi Hillel, who, when asked, how should you lead a good life in society, posed three questions. If I'm not for myself, who is for me? If I'm for me alone, what am I? And if not now, when? Bob Ray liked these three questions so much that he wrote a book called The Three Questions. And he used these three questions, which is a book that's really worth reading. And he used these three questions to explain why he had started out as an NDPer but ended up as a liberal. And it was because initially he was focusing a bit too much on question one, like a conservative. And then he came to realize he was focusing a bit too much on question two, like an NDPer, and wanted to focus on both questions like a liberal. This is why I'm inherently a liberal. Because I'd like to think that you first must look after yourself. No one else should have to look after you. And then once you've looked after yourself, you can look after the world. And if that's the way you believe, you're a liberal. Politics, I can't believe I'm using politics in a science lecture. But the other important thing about this politics statement is that this left-right continuum is not really that important. The real political continuum that's important is this one, the vertical one, the continuum between authoritarian governments and non-authoritarian governments. And I've taken this also from Otto's brilliant 2011 book. And he took it from some guy called Ferris, who I'd like to meet someday. And he pointed out that there's been dictatorships on the left, and there's been, the dictatorships of the people. There's dictatorships on the right. dictatorships of the 1%. And it's whether there's a dictatorship or not that really matters. It's not whether you're left or right. And I completely accept that. But why does this matter to applied ecologists? Well, it matters to applied ecologists because the single best predictor in the world of infant mortality is how free the country is. So an interesting guy called Seymour Gart, who a retired public health scientist in the United States, wrote this interesting book, Where We Stand. And he went to this amazing website that I've since consulted called freedomhouse.org. It's an NGO that every year does this very formal analysis on the state of authoritarian and non-authoritarian governments in the world. And he said, you know, I bet that would predict infant mortality. And Canada is a 7, by the way. 7 is good. And so for 172 countries, he compared how free the country was with infant mortality and then did a whole bunch of other analyses. But I thought, my God, we all also surely would think that if this is true for infant mortality, where children are dying, the environment's probably in bad shape. So can we assemble a similar relationship between environmental condition and freedom? So to do that, we need to link 2 data sets. I'll just take a drink while you're looking at this map. So the first data set is assembled every 5 years by the Yale Center for Environmental Law and Policy and a bunch of colleagues. They look at 59 different metrics of environmental performance in countries. They summarize it into 10 different categories, and they add up those 10 categories. And they come up with dark red being bad, scores around 35 to 40, Central Africa. Green being really good, scores around 80 to 90, Scandinavia, Europe, Costa Rica. Canada's just kind of hanging out in the middle. So 35, 40 is really bad, 85, 90 is really good in terms of environmental performance. Canada's score had sunk because of climate change, the loss of the cod, and one other metric, I forget which. But Canada had drifted down in this metric over the last 10-year period. Is there a relationship between this environmental performance index and freedom? I did this week. When I went back to the freedomhouse.org website, their latest data, maybe they're less confident about giving you all the raw data. They give you is the country free, partially free, or not free? And so that was great. So I was able to match up for 162 countries how the freedom score from freedomhouse.org with the environmental performance index score from Yale University. And in one way, ANOVA, the p-value is 10 to the minus 11. 10 to the minus 11. There's a very, very strong relationship between whether a country has an authoritarian government or not and what the condition of their environment is. And the big change is between free and partially free, not between partially free and not free. I'll just let you think about that. I haven't searched the literature in this area. There's probably a huge literature on this in environmental sociology or political ecology and things like that, but I just thought I'd do a quick version of it myself. But I think there's lessons here. Protect freedom at all costs. And I want to end on a happy note. The most amazing statistic in freedomhouse.org is this one, that they track over the last 40 years what's happening to democracy in the world. And look at this. In the 70s, only 25% of countries were free. Now 50% or 45% of countries are free. The partially free haven't changed. The big change has been with the not free, the collapse of the Soviet bloc and things like that. So there's every reason to be optimistic. If that space for time substitution thing has any predictive power, that as countries become freer and mothers who are worried about the health of their children can influence their governments, that this will be good for the environment. Okay, here's my advice. I'm coming to an end here because it's 1 o'clock. I would be interested in hearing from others, more older guys and gals like me, if they have other advice for young applied scientists. I've just kind of thrown this together over the last week. John said, come and talk about acid rain or recovery or climate change or suddenly I said, no, I'm going to try and do something else. I hope it worked out. I love Wordle. Do all use Wordle? Hope you all use Wordle. So I took all my co-authors. This is my first of 2 acknowledgement slides. So I took all my co-authors and just put that text string into Wordle. So I'm going to thank Bill Keller, with whom I published 25 papers. And you'll recognize who's in the audience. And Charles Ramtran is in the audience. John Gunn is in the audience. Keith Summers is in the audience. Peter Dillon, who isn't in the audience, but did lots of work with him. Will Schreider, who retired a few weeks ago. So I think I've published now with about 160 different people, and Bill is number one. Put your hand up, Bill. Okay. I'd also like to acknowledge the folks here and at the Dorset Environmental Science Center for 35 years of collaboration. Michelle, Aaron, Natalie, and Allegra for the use of unpublished data. John for the invitation. Ken Davey for the Royal Society of Canada nomination. Diane Orhill for her battle to save the experimental lakes area, which may cost her her degree. And here's my second Wordle, which I'll just leave on the board. So I took all my publications for the last, whatever, and threw them into a Wordle. And it does an amazing job of telling you how I've been spending my time for the last 40 years and with whom I've been spending my time. And I thank you very much for listening.